Professor Vivek Polshettiwar, the stage is yours.
Thanks. Thank you very much, Aninda, for this kind introduction and also inviting me to deliver this Bangalore India Nano India talks. So let me share the screen. Can you see the screen, Aninda?
Perfect. Yeah.
Okay. So what I'm going to talk today is about use of nanotechnology to combat the climate change, and with some two specific example where I'm going to show you how to ideally store sun's energy into carbon dioxide using the green hydrogen. I guess we all know the seriousness of the climate change. Climate change is one of the most serious problem mankind has ever faced, and ideally is due to one simple chemical, carbon dioxide. So because of the excessive carbon dioxide, there is a global warming and the climate is changing. Then the solution could ideally be very simple, which is not happening though, which is somehow I capture that excessive CO2 from the environment and not only capture, but convert that CO2 into useful chemicals and fuels, right? So whatever you see around you, which is made up of carbon, should be produced from the CO2. So what will happen then? The CO2, which is in excessive, which is considered as a waste, will be your source of a carbon. And that will make something called a circular economy, where carbon will not be considered as a waste, but it will be part of your different products that we use every day. Now, why there is a global warming? I guess we all know there is a dramatic increase in the CO2 concentration in the environment after the industrialization. And you can see now, it's a very sharp increase. And now on 30th September, when I searched, it's around 416 ppm, which is again highest recorded CO2 level on planet Earth. And because of increase in the CO2 concentration, there's clearly an increase in the overall temperature of the planet. So the planet is warming, the globe is warming. You can clearly see those numbers. There's always some confusion that, okay, maybe we are getting more solar irradiance, and that's why the planet is warming. Not true. We see this constant. The amount of solar photons or energy we're getting is nearly the same within the error bar, but the temperature is increasing. So clearly there is a global warming. And what will happen if the temperature of the planet increases? Clearly, several effects. One of that is melting the ice in Arctic. See, it started with 7 million kilometers in 1980. Look at the unit; it's millions of kilometers. And from 1980 to now in 2000, this data is up to 2015, 7 becomes around 3.5. So 50% of ice is already melted. Now, because of the melting, what will happen? The sea level will increase, right? So you can see now the sea level rise from 1880 to 2017, a dramatic increase in the sea level. And then there is recently a study, obviously it's a modeling, theoretical study, which says that they estimated that 1 billion people now occupy land less than 10 meters above the current high tide lines, including 230 meters below 1 meter. And if the way the temperature is increasing, the way the ice is melting, very soon, majority of these cities will be under the water. This is the just an example of Mumbai city. This is a typical current scenario. But if we continue, this is what Mumbai will be. So most of it will be under the water. So this is a very serious issue. It's not only about change in the environment, which increases the temperature, increases the sea levels, but there are also reports of lots of hidden diseases. They are waking up. The ices which are melting has lots of viruses and bacteria, and they are waking up. They are not dead. They are waking up, and then they found that there are bacteria which are 10 to 50,000 years old, and they are resistant to all the 18 top antibiotics that we have. So imagine if some of these viruses and bacteria come into our life, which are very old. We have no information about their functioning, their molecular structure. So what will happen? So it has a serious impact. The global warming has a serious impact onto the environment, obviously, as well as to the health and the diseases. Now the question is it too late to combat the climate change? Or can we do something, or is it like something is set up and then we can't really stop it? The simple answer that one can says life, the most complex form of a matter in the universe, is on course for its inevitable extinction. It's going to extinct. We can't do anything. Not true, right? Unless we humans, the chosen one, can agree to live within the limits of nature rules. We all agree that we are exploiting the nature like anything, right? We are using the natural resources to its limit, more than its limit. So future will depend on how many people there are on the planet, how we're going to use the energy, how effectively we are and efficiently we're going to use those energy, right? Can we find or can we start using more and more alternative energy resources? Right, so it's up to us what will happen next. But in addition to the typical change in the human's behavior, what a science can do, what a nanotechnology can do, right? And that's what I'm going to show you today, that the technology can also help us to combat the climate change. Now, before I really explain the CO2 chemistry that we do, let me ask one more question, which is, what was the most important innovation of 20th century? I'm sure several of you will have a different answer, but one of the answers could be Haber-Bosch ammonia synthesis. You know, it's a simple reaction of hydrogen and a nitrogen, H2 plus N2, you get ammonia, right? This was discovered in 1909. They observed a very small yield, very small amount of ammonia formed drop by drop, very high pressure, very high temperature, using a radioactive material, right? So this looks like a simple discovery, but it produces ammonia, right? And then Haber collaborated with a Bosch from BASF company, and say within you see discoveries in 1909 and in 1930, within 4 or 5 years, this simple fundamental discovery became a commercially viable industrial process to produce ammonia. And because of that, they got a Nobel Prize. And now, even today, if there is no Haber-Bosch process, we will not have 2/3 of amount of food that we are getting today. So majority of the food that we are seeing now, which is feeding this huge population on planet, is because of Haber-Bosch. That, and please note, this is happening even today. The discovery was 1909. We are in 2022. Even after 100 years, it's the same story, right? And you can see after the discovery of Haber-Bosch process, which provided you ammonia gave you all these fertilizers, and that increases the yield in the farming, right? You were able to produce more food. Now, since you have more food, what will happen? Population increased. You see huge increase in the population. That obviously have an impact on the energy resources, energy use, CO2 emissions, industrialization, right? So if I again ask one more question, what are the challenges of 21st century? I asked the previous question was, what was the breakthrough in 20th century? Now, what are the challenges for 21st century? The answer will be the same. Haber-Bosch ammonia synthesis. Now, why? Although we produce ammonia from nitrogen and hydrogen, but that hydrogen comes from the carbon-based fuel, the fossil fuels, and that emits huge amount of CO2. So this one simple reaction emits, it takes 1% of world's total energy. Whatever the energy the world is using, 1% of that goes to one reaction, which is a huge number. Not only the energy, it also emits around 1% of the global annual CO2 emission. So 450 million tons of CO2 in 2010. So you need to find the alternative to Haber-Bosch ammonia synthesis. And this is just an example. There are processes for cement making, iron, steel, ammonia, traveling, right? Every single process that you see around emits lots of CO2. So now either I can find a way to develop a process where CO2 is not emitted, which is one way to do. Other way is I continue using these processes, but then whatever the CO2 that is I'm emitting should be captured from the environment or from the point it is generated. And not only capture, what will you do only after capturing the CO2? Once you capture that CO2, you should convert that CO2 into useful chemicals and fuels, right? So think about a petrol is coming from the CO2, right? Oil is coming from the CO2. Cement is coming from the CO2, right? Rather than from the fossil fuels. And that's what I'm going to show you some examples of how we do that in our lab, right? And this is not important scientifically, but it's also important for India's path to net zero, right? Even today, 70% of our energy is coming from the carbon-based fuel, right? And so we are emitting the large amount of CO2 because we are growing, right? So we cannot stop development. But then what can we do? Can we not at least capture the immediate CO2 and convert it into useful chemicals? And that requires a breakthrough in fundamental science as well as development of technology where the nanoscience, nanotechnology can help. Right? Obviously, the one solution is I start using renewable energy, right? Solar to electricity, solar to heat. But we know, and solar to hydrogen, but we all know this, the challenges that we face to store the electric energy in the form of in battery, right? The battery is generally lithium based, not that powerful, right? So we're struggling there. We can generate the hydrogen, but then where do I store the hydrogen? Storage of hydrogen is still a challenge, right? So although we need to definitely develop these technology and use as much as we can, but in addition to the renewable energy resources, we must find a way to capture the CO2 and convert them into chemicals and fuels, right? So, and then this is a typical thing that happens in our country, right? We always try to import the technologies coming from outside world, right? Batteries, solar panels, and whatnot. But in the future, it's all about CO2 capture and conversion technology, and we must develop this in our country, right? So what we have to develop is some sort of artificial photosynthesis, right? This is a typical nature, right? You get a photon from the sun, you get a sun energy from the sun, and then the trees, plants take the sun energy, they take the CO2, they take water, and then they provide us all the food, right? What is happening now? We are producing large amount of CO2 because of industrialization. So the trees, the plants that we have on planet will not able to cope up with this excessive CO2. Any number of trees that we plant is not able to take care of the CO2. Obviously, we should plant as many trees as we can, but that alone is not going to solve the CO2 problem because of the limitation of the population and the land required for planting. So what can be done then? Then can we have artificial trees which will do the job of, do the function of a real tree? What real tree does? Again, takes the solar energy, takes the water, takes the CO2 reacts with water, using the solar energy, get you different chemicals, products, foods. Now there's a limitation in the land, water, so many things. So can I prepare artificial trees which will do the same thing? So obviously the artificial tree is is a fancy word. What it is actually a nanomaterial. It is actually a catalytic material which will have ability to harvest the solar energy, capture the CO2, absorb the water and split water into hydrogen, take that hydrogen, add into CO2 using solar energy and get you say methane, methanol, carbon monoxide, different chemicals. And using those basic chemicals, then ideally you can make any chemicals and products that you require. So artificial trees are nothing but the nanomaterials, nanocatalysts. So now I come to the science that we do at TIFR, and I try to explain some of the recent results where we use the concept of nanotechnology to develop some of the catalytic processes. Now, although it looks like a very simple reaction, right? CO2 convert into something else. Unfortunately, CO2 conversion is extremely challenging process. The reason is CO2 is a linear molecule, sp hybridized, extremely stable. C is here. And if I want to react CO2 with any of the chemicals, say hydrogen or alkenes, then it has to cross over such a huge activation energy barrier from CO2 to different products. So that means I need to put very high energy, and that will make the process unsustainable. So what we are trying to do is we're trying to develop a catalytic system, nanomaterials, which will chemisorb the CO2 onto the surface. And once CO2 chemisorb onto the surface, interact with the surface, the CO2 is no more linear, but it bends a little bit. The bond angle changes, bond length changes based on the interaction strength. And that makes that CO2 reactive. And now the activation energy barrier goes down. And then whatever the remaining activation energy barrier is still there, that energy should come from the solar energy, right? So that means I'm using the solar energy, I'm using the nanomaterial, absorbing the CO2, and using the solar energy, I'm going to split the water into hydrogen and oxygen, and that hydrogen will be added into the CO2. So I'm storing the solar energy into the CO2, I'm storing the hydrogen into the CO2. So I not only solve the problem of CO2, but also the excessive hydrogen, the hydrogen storage issue, as well as the electricity storage issue, right? So everything can be resolved by this simple process of CO2 conversion. So what we do in our lab is we develop different kinds of a nanomaterial which has this ability of CO2 capture, CO2 activation, hydrogen activation. At the same time, the same material can also harvest the solar energy. They can also take the photon and convert that into, say, heat or hot electrons, both of which can be used to convert CO2 into different chemicals. So this is one of the examples. This is a Nano Silica. It has a dendritic fibrous morphology. We call it as a DFNS. The particle size can be tuned. It can be 50 to 100, 100 to 200, up to 1200 nanometer. And based on the application, we generally use different different sizes. It has a huge surface area, 500 to 1200 meters per gram. So even if I look at 500 meters per gram, it's like if you take a 1 gram powder in your hand, it's like a 1 football ground in just 1 gram. That's the significant area that you find in these nanoparticles. It has excellent thermal and mechanical stability, which allows you to then develop a processes which is high temperature, high pressure using this material. So we use it for catalysis and CO2 mitigation, but there are applications in drug delivery, sensors, energy storage, and others. So after our invention, which we have patented, after our discovery, say around 10 years ago, now around 150 groups worldwide using this material for all of these applications and many more applications. So this is how the material looks like. These are the electron microscopy, images scanning electron microscopy. They are very monodispersed. You see those are fibrous petals of the flower, like petals of the flower. You see these are transmission electron microscopy images indicating they are fibrous in nature, high surface area, around 600 meters per gram, and very unique pore size distribution. The question that we ask in our lab is the mechanism of formation of these nanoparticles. Why we form spherical fibrous nanoparticle? Why not a solid sphere? Why not a rectangular shape or some rod shape? Why this shape and why this morphology? And generally, it's very difficult to answer because it involves different chemical reactions at the same time to get you these morphology control nanomaterial. So this is the mechanism. What we do is we create a template, and within the template we grow these nanoparticles. So how do we create the template? We use simple organic molecules. For example, in this case, it's a CTAP, cetyl trimethyl ammonium bromide. So this has this quaternary nitrogen group, a polar group. The blue ball represents that polar quaternary nitrogen. And then you have CH2, this long hydrocarbon chain up to 16 carbon, which is a non-polar. So you have a polar head and a non-polar tail. And you can see this is shown here as a blue ball and the zigzag line. So I will show you the animation. So when we add these CTAP molecules, polar head is a quaternary nitrogen, and the zigzag line is this long hydrocarbon chain. We add them into solvent. Solvent is a mixture of water and xylene, 50-50%, polar, non-polar. And the concentration of these CTAP molecules is such that they form these laminar phases. Now we can see that there could be repulsion between the quaternary nitrogens, right? So we added one more molecule, which is the co-surfactant, which is pentanol or hexanol. They reduces the repulsion, stabilizes the interfaces. What we observe is that these interfaces are not floating flat. These are not floating flat, but they are in the form of a microemulsion droplet. They're in the form of droplets. We call them a bicontinuous microemulsion droplet because you have water and xylene continuously trying to mix. So these are the droplets made up of a CTAP, water, and xylene. And this is called the template. So there is no silica right now. But the water channel that you have, it has the silica precursor, which hydrolyzes, polycondenses, and undergo nucleation and growth to form the silica. And then the growth will be confined into these droplets. So if I keep these droplets away from each other, you get a smaller DFNS particle, smaller silica nanoparticle. We also learn to merge these droplets together, so you can get a bigger bicontinuous microemulsion droplet. And if I grow the silica in these bigger droplets, I get a bigger size nanoparticles. So that's how we were able to tune the particle size, say from 50 nanometer to up to 1.2 micron size, 1200 nanometer. And then we try to explore this material for range of application. I'm going to give you some in the brief and 2 examples in details today. So one of the example is use of defects in creating the active sites. So right, silica is a SiO, simple amorphous random network of silicon oxygen. So we call it siloxane. What we did, the question we ask is, what if I break these SiO bond? Then I get an Si radical, oxygen radical. Can they activate the CO2? Can they dissociate the hydrogen? What if I break both SiO Si bond? Then I get an oxygen vacancy. See here, it's Si, no oxygen is missing, and then Si. So what will happen if I create an oxygen vacancy, and whether these sites, oxygen vacancies, Si radicals, oxygen radicals, whether these defect sites will come together, work cooperatively to activate CO2 and hydrogen. And indeed, that's what we observe, that if you can create a proper types of these sites with the proper proximity, they work together to dissociate the hydrogen, activate the CO2, and then CO2 is converted into methane. No need of any metals, no fancy expensive materials, only the silica. In another example, we showed that by replacing one of the aluminium, not one, some of the aluminium from silicon. So SiO, so it's now SiO aluminium. And that makes this material strongly acidic. The acidic strength of this material is very close or nearly close to zeolite, which are known to be the strongest solid acid. But zeolite has these micropores. Not all the molecules can diffuse into micropores, less than 2 nanometer, whereas ours has a wide pore size distribution up to 15, 20 nanometer, so that even the bigger molecule can diffuse in and you can do different catalysis. I showed you one example, but we try to do range of catalysis using this solid acid material. We also develop CO2 solvent in our lab, where you can either capture the CO2 at a lower temperature after it comes from the industry, or you can capture the CO2 at a high temperature while the CO2 is produced in the reactor. You don't need to wait for the CO2 to come in the environment and pollute. Capture it as soon as it is produced. So both the processes we have recently developed. So these are some of the brief introduction of my group, and now I will try to present one or two work in detail. If you want to know more about the DFNS, you can then refer to this accounts of chemical research that I recently wrote. Now, the part one of my talk, the more detailed work, is about the concept called plasmonic catalysis, where I can generate hot electrons in the black gold, and that can be used as a catalyst, a green catalyst, to convert CO2 into useful chemicals. Now, what is plasmonic catalyst? So there is a concept called surface plasmon resonance. For those who don't know it, we know the metal is very shiny. Why? Because metal has this electron cloud onto the surface. It reflects most of the photon coming from the sunlight. In case of gold, it's a very golden color because it absorbs some portion of the blue light. Rest of the light is reflected, and that's why it has this the golden tone. But when you reduce the size of the bulk gold to a gold nanoparticle, that electron cloud no more reflects the light, but it starts resonating with the light. Right? The light has this electric field, and you can see this is the electron cloud onto the gold nanoparticle. So based on the direction of the electric field, it will start resonating, and there will be resonance at one particular wavelength. And this is the typical, basic, simple explanation of surface plasmon resonance. Now, more exciting thing happens after the particle undergoes the surface plasmon resonance, because at one point of a time the coherence will break, and then whatever the photons, whatever the energy is involved in the surface plasmon resonance will get damped onto the gold particles. Now the gold particle is able to harvest all those photons onto its surface. So now gold surface has a large amount of extra energy. What will happen to that? What will be the changes in the gold particle? So we know the metal has the large number of electrons at the Fermi level. So the photon energy is used to excite the electron from above Fermi level. So electrons will get excited to Fermi level by different mechanisms, S2S and D2S transition. D2S is obviously prepared pathway. Now you have the electrons. So this is the EF Fermi energy level. So you have the electrons above Fermi level. We call them excited electrons. More typically, it's called the hot electrons. Now what we can do is we can take these hot electrons and inject into the CO2 molecule. We know CO2 is stable, but once I inject the electron into the CO2, it becomes CO2 radical anion, and now it is really reactive. And now it can react with any different chemicals and convert into different chemicals and fields, right? So that's the plan. Use these hot electrons in the nano gold to convert CO2 into something. Unfortunately, the lifetime of these electrons is very short, less than tens of femtoseconds. So the electron combined with these holes and doesn't really go to the CO2 or any other organic molecules, right? So this particular hot electrons is not really used, not possible to use. But then there are secondary relaxation processes that happens in this field, in this process, where these hot electrons undergo electron-electron collision with the electrons which are already, some of the electrons which are there at the Fermi level. And these electron-electron collision again excite the electron at the Fermi level to some higher energy level. These are called the Fermi-Dirac distribution or warm electron, some sort of a secondary hot electrons, having a better lifetime. And then you can ideally able to transfer these hot electrons and ideally transfer those electrons to the CO2 and convert CO2 into useful chemicals. If you cannot even use these hot electrons, then these hot electrons undergo electron-phonon coupling. Like phonon is a vibrating atom, so the electron collide with these vibrating atoms, and all the energy that was absorbed from the sun is now converted into a thermal energy, which is localized onto the surface, onto this gold nanoparticle surface. So if my reaction is happening onto the surface, then that reaction will get this energy and reaction rate can increase. So you can have a hot electron assisted reaction or a photothermal assisted reaction. Now, only problem with these processes is the typical gold nanoparticle or silver particle, if you make it, say 5 nanometer, 10 nanometer, they absorb only some portion of the visible light, some portion of the sunlight, say around 550, 530 nanometer. But if I really want to develop a photocatalytic system, then I need to absorb entire solar spectrum from visible to near IR. I harvest large number of photons so that I can produce large number of hot electrons, transfer them to CO2, and ideally that will get you a better CO2 conversion. Now, how do I develop a material which absorbs broadband light absorption? So ideally, it was not possible previously, but then we came up with a process where the hypothesis was if you bring these nanoparticles closer and closer, the electron cloud of these gold nanoparticles interact with each other. Two several come together and they interact with each other. That's the plasmonic coupling. And that allows you to have a broadband light absorption because then entire clouds start resonating with several particular wavelength of light or a broadband light. Now the question was, how do I tune the particle size, gaps between the particle size? I can tune the size, shape, morphology, well known. What about the gaps? How do I play with the distances? What we did is we took the silica sheet. I'm showing you a silica sheet. We took a DFNS and now think about one of that fiber is this. We loaded that with a gold nanoparticle, nicely distributed. And then in the second cycle of a nanoparticle growth stage, what we did, we loaded or we tuned the concentration of a gold atom by reducing the gold precursor with a formaldehyde. The concentration of gold atom is below supersaturation. That means the gold atom will not undergo nucleation and growth. They will not able to form the nanoparticle by themselves, but these gold atom will grow and have a growth of an existing gold nanoparticle because of the better weighting factor of the gold atom onto the gold surface. And that way you can slowly increase the size of these gold nanoparticles. Size is increasing, right? And so that will reduce the gaps between the particles. And that's what we did. We did several cycles because we don't know what is the best optimized gap. So we try to make series of materials to find out what is the best gap that one can have to get a broadband light absorption. And now what you see here, this is the typical light absorption when the particles are away from each other. But with particle coming closer and closer, you see now the light absorption is becoming broader, right? And it's actually absorbing now from 400 to around 1100 nanometer, entire solar spectrum in the visible and near IR light. So that's a good thing, right? We want to have lots of photon get harvested so that I produce large number of electron, inject into the CO2 and convert that CO2 into useful chemicals. Now, another interesting thing that we observe is the gold becomes black. The reason is it is absorbing all the sunlight, right? So it has to become black. And note, the gold is still metallic. There's no change in the oxidation state, no doping, no hybridization, no functionalization. It's a pure metallic gold, but still it is black in color because of these interparticle plasmonic coupling and particle size. So we were very excited. We thought, okay, we made a material which is black in color, which absorbs a large number of photons, then it should show a good photocatalytic activity. So we carried out this reaction, CO2 plus water, some sacrificial reagent to get you the methane. And the activity with the C4 is around 1.5 micromole per gram, which is 10 times better than the normal gold particle. If you take a normal gold particle, the activity is low. So in that sense, it looks like black gold is working. However, if you look at the number again one more time, it's just 1.5 micromole per gram. This is negligible. It's very minute. If I really want to make this process sustainable and commercially viable, doesn't look like. So then question we ask is, why? If material is so black, it absorbs large number of photons, then ideally it should show good catalytic activity, which is better than a normal gold particles, but not really significantly better. So the only way one can answer this is, although we are harvesting lots of photons, although we are generating large number of hot electrons, possibly the lifetime of these hot electrons is still short. They are coming back and combining with the hole and not getting injected into the CO2. So that was the reason for that could be the reason for the low yield of the product. Then the question is, how do I increase the lifetime of these electrons? I know how to produce them in large quantity, but how do I increase the lifetime? So what we decided then, that let us make some sort of a heterojunction, some sort of a bimetallic system, where in one metal, which is black gold now, once the electrons are generated, they jump, they get injected, transfer into the unoccupied state of another metal. So electron is in one metal, hole is in another metal, right? So they are separated. That should ideally increase the lifetime, and that should allow you to get a better catalytic activity. So to prove this hypothesis, to study this hypothesis, we then designed a catalytic system where we loaded the black gold. This is the work done by my PhD student Rishi Verma, and this is still unpublished. So the black gold is loaded with a nickel side, and now you have a gold. We have a gold and then the nickel sides, right? So electron is generated in the black gold and then it goes to the nickel, and nickel becomes my reactor, right? Antenna is the black gold, which takes all the photon, gives the electron to the nickel, and nickel becomes catalytic. Nickel take the CO2, nickel take the hydrogen and this electron and react CO2 with hydrogen to get you different products like CO, methane, and other products. This is how we synthesize the material. We prepare the black gold, loaded with the nickel salt, reduced by sodium borohydride, followed by S2 reduction, and we got a small nickel nanoparticles. Although we were not able to see the nickel nanoparticle in the normal imaging because of the similar contrast between the gold and nickel, but when we did the elemental mapping, we were able to clearly see that nickel is, uniformly loaded onto the black gold. Right. And then we also wanted to know whether there is a change in the light absorption behavior of black gold when we load it with nickel. So DPC is another technical name of the black gold, is dendritic plasmonic collidosome, which is known as the black gold. Now you can see when I loaded the nickel, there is no change in the light absorption. It's still a broadband light absorption. XPS and IL says that the nickel is in 2+ state, which is ideally not possible because we have reduced it. So there was this confusing result. But then we realized that XPS and ILs are done in open environment. And if my nickel sites are really small, very ultra small nanoparticles, then they will oxidize and you will always see 2+. So then we carried out this CO titration in a glow box in inert atmosphere using the drift experiment. And we realized that the CO is chemiswapping onto the nickel, monodentate or a tridentate way. And you get these two signals at 2028 and 1998, which clearly indicate that nickel is in a 0 state. And there could be some amount of nickel 2+ for sure. In addition to these hot electrons and thermal energy, you also have this polarizing electric field that is produced during the surface plasma resonance. And now, between the two particles, between the gaps of these particles, that's why we call them hotspots, electrical hotspots. Now, if your reactants are in these electrical hotspots, then these reactants will get polarized. CO2 will get polarized. CO2 will bend. CO2 will bend. The bond length will change, and that will again activate the CO2, and your activation energy barrier will go down, and you may be able to do the reaction at lower temperature only simply by using the hot electrons. So you can see there are several things that are happening positively when I use the concept of surface plasma resonance. This is how we do a catalysis. We have this and quantify using this online system. These are the results. First, we carried out the blank dark reaction, no light, black gold nickel, no light. You can see 84, 136, up to 223 degrees Celsius. We observed no activity. However, as soon as we switch on the light of a different intensity, say 2 watt per centimeter square, in between 2 to 3 watt per centimeter square. So as soon as we switch on the light and kept increasing the light intensity, we clearly observe extremely good yield. See now, if I look at this around 2.2 or 2.5 watt per centimeter light intensity, the yield is around 2,200 millimole per gram. See the number, millimole per gram. The number I showed you previously is a 1.5 micromole per gram, which suddenly jumps into millimole, that to around 2000. So you can see a dramatic change in the catalytic activity by simply tuning the catalyst design. So that's the beauty of nanomaterials and possibility of tune their properties by simply making these heterojunctions and defects and interfaces. We carried out several control experiments, and clearly it's only the black gold nickel which was active. We also carried out this labeled experiment where rather than taking CO2, we took the labels, 13 labeled CO2 to prove that the product is coming really from the CO2 and not from impurities. Catalyst stability is very important thing in the field, right? So you want to convert CO2 not only for some time, but for hours and hours and days actually, right? So that the same material can be used for converting large number of CO2 into useful chemicals. So obviously we cannot really test it for months, but we tested it for 100 hours. And you can see that the catalytic activity is nearly the same for 200 hours. It's very stable, clearly indicating that this is a stable system with a very good production rate of CO. So that means it has the potential to be used in a sustainable manner. Right? When we compare our numbers with the all other reported numbers, we are far better. So the best number in the flow is 13.5, but we're getting is 2464 millimole per gram per hour. So there's a dramatic increase in the numbers. And there's several fundamental aspects that we discussed, but I have only 10 minutes left. I will not go into the details of this, and I will show you one more project which is simpler but more sustainable. And then we try to understand whether the reaction is really because of the hot electron transfer or is because of the localized thermal heating. Carried out range of different experiments. This one experiment itself proves it, right? In the dark, there is no activity. At the same temperature, in the light, it has activity. Clearly, it has to be the light assisted and not the thermal. Still, we carried out different other experiments like pheromone thermometry to measure the surface temperature, and we observe that temperature can go only up to 150. This is the other way of measuring the surface temperature. So this again indicates that it has to be hot electron mediated. We also carried out an experiment where we put more and more photons, so more and more light intensity. So if I expose the black hole with more and more photons, ideally I will get more and more hot electrons. And if it is really a hot electron mediated reaction, then kinetics of the reaction should also increase if I'm putting more photon and more generating more electron. That's what we observe. With increase in the light intensity, there is a linear relationship between the light intensity, number of photons, and the production rate, indicating again that it is the hot electron mediated reaction. We also calculated activation energy barrier. So see, in the dark, activation energy barrier is 0.68 eV, whereas in light, it is 0.22 eV. You see a dramatic decrease in the activation energy barrier. And now see, that's why this reaction is happening at a very low temperature, at a room temperature ideally. We also try to understand the mechanism, how the CO2 is dissociating by the in situ studies. I will skip this. We also try to prove that the electron is really injected from gold to nickel using these ultra-fast techniques in collaboration with Jacinto. And these particular bleach signal clearly indicates that nickel is transferred from electron is transferred from gold to nickel, and that's why there is a bleach here. I'm not again going into the details, save the time. And we also use this material to carry out other chemical reaction like dichloromethane to methane, hydrogenation of propene and acetylene. Ideally, you can use it for any hydrogenation reaction that you think is useful. Right. So conclusion of part one is I showed you this system called black gold nickel, which we call antenna reactor system. Black gold as antenna, absorb all the photon, generate the electron, give it to the reactor nickel, and the nickel does all the CO2 conversion. We still have some unanswered question in terms of electron transfer and all of those that I will skip now. And I will come to part two and take around 10 minutes to answer 10 minutes to present this. So I showed you this process of a black gold nickel capturing the CO2, converting into useful chemicals. But at the same time, it's complicated, right? The synthesis is complicated. You use this expensive gold, right? So this process may not be really sustainable if I were to really commercialize it. So one should ask this question then, what should be the characteristic of the process that will really be commercially viable? At the end of the day, CO2 is a real problem. Climate change is a real problem. I cannot just keep publishing the papers. I also need to come up with the processes. And we realize that more the complication, very minute chances of then going into the commercial value. So if I want to list the characteristic of a dream process of CO2 conversion, then the CO2 conversion is the process should happen at an ambient temperature and pressure. I don't need to give any external temperature or external pressure. I don't need to give any extra energy. It should happen at room temperature. I don't need to even produce hydrogen and then use that hydrogen cylinder. Can I use water as a hydrogen source, and during the reaction somehow the water splits into hydrogen and give me proton or hydrogen? And most importantly, it should be the process should use inexpensive and abundant material, not gold, platinum, silver. These are all we know limited, expensive. Can I use something which is inexpensive and abundant? So this looks like a dream list. It looks like this will never be achievable because we know CO2 conversion needs very high energy. So why will it happen at a room temperature? Theoretically, it seems impossible. We luckily came across this process. What we observe is, if you take a magnesium nanoparticles in a water and just bubble the CO2, all the CO2 reacts with water and magnesium and convert that CO2 to methane, methanol, formic acid, hydrogen, and magnesium basic carbonate. A very simple process. Think about a glass of water with a magnesium powder and bubble the CO2. Done. You don't need to heat. This is happening at a room temperature, at atmospheric pressure. You don't need to heat. You don't need to provide any light, no electricity, nothing. And you don't even need a hydrogen gas. You need a water. The water can be seawater, wastewater, anything, and still you are able to convert that. And by the way, magnesium is the fourth most common element in the Earth. Earth mass is around 30% is made up of magnesium. So it's the fourth element after iron, oxygen, silica. So you can clearly see this is a very neat and clean process happening at a room temperature. However, there is one catch that this process has, one negative aspect of this process has, that I will show you after 2 slides. So, and the reaction is very fast. If I take air, well, by the way, you don't need to take a CO2, pure CO2. Even you take bubble the air, glass of water, magnesium powder, bubble the air that you see around, you still get these chemicals because air has 400 ppm CO2, and this reaction is so fast happening at room temperature that even the CO2 in the air is getting converted, right? It's called direct CO2 conversion. And you look at the rate of the reaction. If I'm taking air, within a few minutes, you convert all that CO2 into methane. If I take a pure CO2, it takes around 10 to 15 minutes. Obviously, at this scale, which is a small scale, this at a lab scale, but you can clearly see this reaction is very fast. And we carried out several other experiments to prove the mechanism. To prove the mechanism, we did 13 NMR studies, FTIR, XPS, lots of in situ studies. I'm not going into the details because I know we want to have an overview of the material, the research. So, but we wanted to know how the CO2 interacts with magnesium, how the water interacts with magnesium, how come they are reacting at the room temperature. We studied that. So while this process was happening, we were using this ATR, FTIR, and the DIPS-IR to understand and see what are the intermediates are formed. And based on that, we came up with this proposed mechanism. Several of these steps are seen in the IR, and several of them are not seen in the IR. So that's why it's still proposed. So magnesium reacts with CO2 and water together. If CO2 is absent or if water is absent, reaction doesn't happen. It has to be together. So it forms this basic magnesium carbonate, and then it takes electron from magnesium, proton from water, keep adding electron, proton, you get a formic acid, adding more electron, proton, you get methanol, keep adding, you get methane. And obviously the selectivity of reaction is towards the methane. It doesn't really produce large amount of acidic formic acid or methanol. This goes quickly here. Now the drawback that I said to you is, although this entire thing is catalytic, but magnesium is also reacting with water and forms magnesium hydroxide, and then the CO2 reacts with magnesium hydroxide to form this magnesium hydroxide basic carbonate. So at the end of the day, at the end of the reaction, all the magnesium is used up for this magnesium basic carbonate formation. So overall, the reaction is no more catalytic because now magnesium is no more there, it's converted. Obviously, there is a way where I can convert these magnesium basic carbonate into the magnesium using solar energy, but that is also a very complicated process. So that's the only negative side of it, that magnesium is being used, it's not catalytic. So as soon as you say the process is not catalytic, what we think, it's non-sustainable, right? Because I'm utilizing using of the magnesium. But it's not always true. It's always not always true. Even if the process is non-catalytic, the process can be sustainable. So in order to do that, we calculated some sort of a sustainability. So 1 kg of magnesium produces 2.43 liters of methane, 940 liters of hydrogen, 3.85 kgs of magnesium basic carbonate. So even I say, okay, methane, methanol is not my product, and magnesium basic carbonate is my real product. Obviously, you are converting CO2 into these, so they have their own value. But look at the magnesium basic carbonate. It's 3.85 kg from 1 kg. And basic carbonate has lots of applications. It can be used in green cement, building material, pharmaceuticals, anti-acid that some of you may have taken. It has this magnesium basic carbonate and different applications. So another thing that we observe now, which is a very interesting thing, that you really don't need a magnesium nanoparticle in this process. You can use the bulk magnesium. In fact, we went one step further. We said, can I use the magnesium scrap, the waste that is lying around? And we purchased some scrap from the supplier, it's 700 rupees a kg, converted that into some sort of a powder, not a nano, just a powder, bulk powder that we see around. And still the reaction works with little slow rate, but it's anyway at room temperature. So the energy is not required. So it's okay. So no, you can see 1 kg magnesium in 700 rupees, 3.8 kg of magnesium basic carbonate is 7,700 rupees. So look at the calculation. So this is obviously far away from our science that we're discussing, but this process seems to have a very commercial, viable, and then we are now collaborating with Adani to really take this to a next level. So the challenge is always that this whatever I'm showing is at a large scale. So we have to show it at a bigger scale and maybe kg scale or several kg scale, and then at a pilot plant. But we're trying to do that. Right. So skip this. And there are lots of magnesium in our country, across the world. Huge amount, 870 kilotons of magnesium is produced per year, and a similar amount of scrap will be is there, and I can then use that scrap. I don't really need any energy. Water can be seawater or wastewater coming from the industry. So it's a very good concept of waste to wealth. CO2 is waste right now. Magnesium is waste. Take both of them. Water is also there, right? And you get a green cement. So ideally, 1 kg of, if in a conventional way, if you produce a 1 kg of cement, you emit around 2.5 kgs of CO2. Here it's the other way around. I produce 3.2 kgs of cement from 1 kg of magnesium, and I mitigate 2.2 kgs of CO2. Just opposite. So you can imagine if every cement industry starts using this, because cement industry is the biggest polluter, right? In addition to the steel. So they can use this process. In addition to that, we also showed that we can produce large amount of hydrogen, 940 liters of hydrogen. Look at this data. If I use pure magnesium without and water reaction, no CO2, then I only produce 2.24 liters. But as soon as there's a CO2 in the reaction, then I produce 940 liters of water. There's a chemistry there, right? When it's magnesium and water, it forms a magnesium hydroxide layer onto the magnesium, and then internal magnesium atoms cannot react with water. But when I form magnesium carbonate, basic carbonate, in presence of water plus CO2, that magnesium basic carbonate layer can dissolve into the water. And then the fresh atomic layers of magnesium is ready to react with the water. And that's why entire magnesium gets reacted with water very fast. You look at the kinetics within a few minutes, and you produce huge amount of hydrogen. And now then think about some dream apparatus device where I have these cartridges filled with a magnesium powder. Again, no nano, bulk, scrap magnesium. Then I have 2 tanks, one with water, another is CO2. And then you mix water and CO2, add into the magnesium cartridge, and you produce the hydrogen. The flow of hydrogen can be then tubed by flow of CO2 and water. A very simpler system. We're trying to find a collaborator to build it. Right. With that, I'd like to conclude. I'd like to thank Karnataka Science and Technology Promotion Society for giving this opportunity, and obviously India for hosting me here. And the funding sources, Department of Atomic Energy. Most of our funding comes from the Department of Atomic Energy. We also have some funds from Indo-French TIFR, Shell Industry, HPCL, BASF, and this multinational mission innovation. The black gold work I showed you is done by Rishi. Magnesium work is done by Rajesh and Sushma, and these are other students that I have. That I like to thank you very much again for listening to me, and more than happy to answer the questions if you have any. Thank you.
Yeah, yeah. Is Vivek, thank you very much for a wonderful talk. In fact, I learned many things, and it's very simple and such a it's so productive and application oriented thing. And as you said, so many patents and working with Adani's group and so on. So I really looking forward to this great future of this kind of research
Thanks, Sanjay.
activities. Okay, yeah. So the now is open for questions. So if there are questions, someone have any questions, they can unmute and ask directly, or they can chat. Is there any question?
Excuse me.
Yes.
Yes.
Go ahead.
Yes, sir.
Yes,
Sarvesh here
Sarvesh.
from Pune, MIT ADT University. Sir, actually, the next research you showed us about the magnesium. I just wanted to ask you that you have researched in this field for a long time. I just wanted to ask you that in biofuel, what do you think we actually can do uh, to reduce the cost of the production, unit cost of production, and make the complete system efficient?
Hmm. Obviously, this is out of the scope of my expertise, right? I don't work in the biofuel, but I think the basic thing is again the same, right? How do I use the waste bio product, right? Rather than using the plants and food, which gives us the food, right? That's one of the biggest challenge of a biofuel, right?
Right.
You cannot use the sugar cane to produce ethanol because that's giving us the sugar, right? So either you take a sugar or the ethanol, something like that. So somehow, if you can find the waste in your farming, right? And if that waste can be converted into the fuel, that will be sustainable. Exactly, you can reproduce the magnesium story in there also.
Right.
Right.
Okay, while others are asking, let me, okay, it's another query. For the second part, this magnesium powder, as you said, it doesn't require neither nanoform or any particular, I mean, it doesn't depend on the morphology and all. It's like a, as you say, scrap when it's working. So I
Yeah.
was wondering, so why nobody, I mean, why it has not been seen for edges, like, magnesium and water? It looks it's so simple. Right.
Yes, that's good. In fact, when this happened, I never believed that this is happening.
Yeah.
I tell you the story. So the way we started the project, we were working on this blackboard as a plasmonic material, and then we said, okay, let us find a way where I replace the expensive board by some cheaper but a plasmonic material. And during the same time, there was ACS Nano saying that magnesium is plasmonic. The first report, very first, 2-3 years ago. We said, wow, this is a perfect for us. So we made the magnesium nanoparticle and carried out the reaction in the light, like the blackboard. The reaction worked. I said, wow, the concept is working, right? But the next thing that we do, you do the control, right? Without light.
Uh-huh.
Without light, things are working.
Also working.
Yeah, then it's strange. I said, how can that be? And then we realized the color of the product, the magnesium, which is a black color, during the reaction, it becomes white. I said, now that means the magnesium is reacting by itself, right? It's not really a catalytic. And then we tried to characterize, and then we realized that it's completely different chemical reaction there, right? So magnesium plus water is well known. There are lots of processes where people produce hydrogen from magnesium plus water. But then the yield is very low because once magnesium reacts with water, it forms this magnesium hydroxide, and its reaction stops there. And luckily, we found that if you have a CO2, it forms carbonate, peel off, right? So maybe we are lucky to find that. Nobody before.
Yeah. Okay, that's the catch. You are saying that magnesium hydroxide is basically like an aluminum oxide. So it's a top surface. Basically, you have a coating, and then you can't access all your molecules.
Exactly.
So,
Yeah.
but once you convert to magnesium carbonate, so basically you utilize all the atoms to
Atoms of the
convert to
magnesium.
oh,
Yeah.
that's the beauty. Yeah. Great. Okay, there was somebody post some. Okay, so there is someone has posted Amores. He's asking have you observed any reverse reaction between carbon dioxide and H2O? And also effect of H2O on reaction kinetics as the reaction proceeds?
So the two questions. The first one, we did not observe the reverse reaction. In fact, we wanted there could be some reverse reaction so that magnesium can be generated. But no, it requires very high temperature, or you have to use electrochemistry to really reverse the reaction. In terms of the effect of water on the reaction kinetics, we haven't really studied, but we are really using water in excess. So at this scale, I don't see an effect of water, but maybe if I reduce the water to a lower and lower scale, maybe at one point of a time, water, it will have an impact, because the water is one of the reactant molecule. Water is also one of the solvent molecules, so it will have its impact on dissolution rate of the basic carbonate from the magnesium, and that will indirectly have an impact onto the reaction kinetics. But we were working with excessive water, so we never observed that.
Okay, so while maybe we can wait for one more minute or so. So while others are asking, let me ask you your first part, this what do you call it? DFNS.
DFNS, okay.
So there, the morphology of your that silica nanoparticle. So what is the role of morphology? It's just a large surface area, or making this gold nanoparticle distribute, different kind of distribution, which gives you all this wide broadband. You said, yeah.
So it has a very critical role, right? In fact, after the discovery, first 5 years, we in fact showed how the morphology plays a role in different applications: catalysis, drug delivery, CO2 capture. I can give you one simple example. So the typical high surface area material, say SBA15 or MCM41, these are like a solid sphere, and you create a hole into it. So when you create a hole, that means I have one entry and one exit. So molecule can enter from one and exit from one. So it has a diffusion issue, right? It's a diffusion barrier. So what we did, we opened it up. Now this is my pore. I can enter from top, here, from everywhere. The reactant can enter from here, the product can enter from anywhere, and that helps us increase the catalytic activity is very, very dramatically, because now molecule can go from anywhere. Another problem was when the conventional material, you have this pore inside, my active site is inside. So reactant has to go in, see that active site, and then react. Now it is open. Active sites are openly exposed, and that helps us in typical thermal catalysis. In light catalysis, photocatalysis, because of the fibrous nature, when photon goes in, before it comes back, it will start reflecting, lots of internal reflection. That means photon is staying more in the material, and then my material get a more time to harvest those photons, right, and convert into electrons. So that was the advantage in a photothermal. And then when you want to make such a dispersed, a distributed material, where I can distribute nanoparticle, tune the distances, this is not possible with a normal porous material. It has to have open system. So there are several other nice use of these.
Yeah, no, I understood. Yeah, it's fantastic. So how did you discover this nano? It's just there was a I mean,
yeah, good question. So this is always the interesting stories behind all these new materials.
Yeah.
So when we started this project, we wanted to solve this problem of opening and one end.
Yeah.
So we said, okay, let us make a hollow sphere, right? And then some holes on the top so that everything is empty. So we started the way the work in the material science, that we come up with some hypothetical experimental conditions and start making the material in the lab. And even they fail, that the experiment teaches you lots of things, and then you again tune the experimental condition and try to get that product. What we observe at one particular time, that we're getting those hollow sphere, but we're also getting these star-shaped particles somewhere as an impurity, maybe 1%. And then it clicked to us that this seems to be better for solving our problem than the hollow sphere. So we kept optimizing the conditions so that we only get these fibrous particles, right, based on our expertise in the synthesis. And that's how we came up, we developed this material.
Great. Yeah. So, is there any questions from the audience? Please, you can unmute and you can directly ask the speaker. Seems like. Okay, I don't see any more questions, and we are beyond the time.
Yeah.
Vivek, very nice talk. Thank you very much for accepting our offer as well as giving such a nice talk.
Thanks.
And I'm really learned many things, and it's really interesting, very interesting, and has a very great. I look, as I said, looking forward to great application in future.
Yes, yes. Thanks, Anindya.
Yeah. See you then. Bye bye.
Hey, bye-bye.
Yeah. 1 second, Dr. Venkatesh,
Yes, sir. Yes,
you
sir.
want to
Yes, sir.
formally close this meeting?
Yeah, definitely, sir. Distinguished participants, ladies and gentlemen, good evening to everyone. At the outset, it gives me immense pleasure to propose a vote of thanks for all the participants of the third Nano Talk of Bangalore, India webinar series. We wish to express our sincere thanks to Professor Vivek Polshettiwar, Associate Professor, Tata Institute of Fundamental Research, Mumbai, for today's excellent, informative and application-oriented talk. Thank you very much, sir. Our special thanks to Professor Anindya Das, convener of Bangalore India Nano Talks 2022, and Associate Professor, Department of Physics, IAC, for his valuable guidance in planning the Bangalore India Nano Talks. I also thank all the distinguished invitees and participants of this program, and we look forward to your continued support and participation in the Bangalore India Nano Talks 2022. Thank you, one and all. Thank you again. Thank you.
Thank you, everyone. Thank you, Anindya.
Bye bye.
Bye-bye.